All right, let's just dive right into this. Welcome everyone to today's Explainer. Today, we're unlocking one of the most powerful and honestly kind of mysterious areas of artificial intelligence. We're stepping into the world of unsupervised machine learning. You know, in our past deep dives, we've usually talked about having an answer key. But what happens when you have literal mountains of data and absolutely zero answers? Well, let's jump straight into this mystery and figure out how to be data detectives.
I absolutely love this quote we have here. Staring at raw data until the patterns reveal themselves. I mean, it just perfectly captures the core challenge, doesn't it? When we're doing unsupervised learning, we are quite literally acting as detectives, trying to solve a case without a single initial clue. No eyewitnesses, no confessions, nothing. The data definitely has a story to tell, a hidden structure, but it's entirely up to us and the algorithms we deploy to pull that narrative out of the noise.
So that brings us to a massive question. How on earth do you find patterns when you don't actually know what you're looking for? Really think about that for a second. Out in the real world, labels are incredibly expensive and time-consuming. Imagine a hospital with, say, millions of patient records. Literally no one has the time to go in and manually tag every single one with a highly specific disease category. Or think about a cybersecurity team watching an endless river of network logs. Nobody's sitting there flagging every weird anomaly by hand. We absolutely have to group this similar data without any human guidance.
And that clearly illustrates the stark contrast between the two main worlds of machine learning. Supervised learning? Well, it's a lot like learning from a textbook where the answer key is sitting right there in the back. You make a guess, you check the back, and you correct yourself. Unsupervised learning, on the other hand, is all about discovering hidden structures completely without those labels. We're essentially forced to grab our algorithmic magnifying glasses and uncover these groupings and structures entirely on our own.
Moving to Section 1, the workhorse, K-means clustering. Let's crack open our detective toolkit and look at our very first tool. The absolute core of K-means clustering is this concept of a centroid. When you use K-means, you're essentially asking the algorithm to divide your data into exactly K number of clusters. And each of those clusters has a centroid. Think of it like the center of mass, or maybe the gravitational pull for that specific group. Every single data point looks at the board and gets pulled straight towards its nearest centroid. It's actually a really intuitive way to slice up information.
Let's break down how this works in practice with something called Lloyd's algorithm. It's a super elegant four-step loop. Step 1, we just randomly drop K centroids right onto our data map. Step 2, every single data point gets assigned to whichever one is closest. Step 3, and honestly this is where the magic really happens, we recompute that centroid by finding the actual mathematical center of all those assigned points. Then, Step 4, we just repeat. The centroid moves, some points might jump ship and change allegiance to a new centroid that's now closer, and we keep looping until the whole thing settles down. What we're doing here is minimizing inertia, which is really just a fancy term for the squared distance from the points to their centers. Basically, we want those groups packed in tight.
But hold on. How do we actually know what that magic number K should be in the first place, right? Since we don't have an answer key, we have to grade the algorithm's homework ourselves. And that brings us to the elbow method. You literally just run K-means for one cluster, then try 2, then 3, and so on, and you plot out the inertia. As you add more clusters, the distance naturally drops. But eventually you hit a wall, a point of diminishing returns. It looks exactly like an elbow on the graph. And that bend? That's usually your optimal number of clusters.
Now, if you want a slightly more precise grade, we can bust out the silhouette score. This is a brilliant little metric that scores your clusters from -1 to +1. It calculates exactly how tight a point is to its own cluster family compared to the very next closest cluster. A score close to a +1? That's great. It means your data points are hugging their centroid super tightly and they're well separated from the rest. But a negative score? Yeah, that means your point is probably sitting in the wrong cluster altogether.
Let's jump to Section 2, the shapeshifter, DBSCAN.
So K-means is a total workhorse, for sure, but it does have a bit of a fatal flaw. It assumes every single cluster is a perfect sphere. Imagine a scatter plot. If your data happens to look like a long, winding river instead of a round pond, K-means is just going to blindly chop that river into circles. Not great. That's exactly where DBSCAN steps in. Instead of hunting for perfect spheres, this algorithm is all about looking for dense crowds of data. It assigns points a specific neighborhood status based on a search radius, which we call EPS, and a minimum crowd size. A core point is right smack in the thick of a dense crowd. A border point is just hanging out on the edge of that crowd. And a noise point? Well, that's just an isolated straggler out in the middle of nowhere. By connecting all these core points together, DBSCAN can map out clusters of literally any bizarre, irregular shape you throw at it. Next up is Section 3, the tree builder, hierarchical clustering.
What if your data isn't just grouped into flat, distinct categories? What if you actually want to see how everything relates at multiple different levels, kind of like a giant family tree? Well, the output for that method is a dendrogram. We use a bottom-up approach for this one. I want you to imagine starting with every single data point acting as its own tiny isolated cluster. The algorithm scans for the two closest points and simply merges them. Then it finds the next closest pair, merges those, and so on. It continuously builds up this massive tree diagram, showing you the exact distance at which things merge together. The sheer beauty of the dendrogram is that you can literally take a slice through the tree at any vertical level you want. That gives you either large overarching categories or super specific subcategories, all without having to guess the number of clusters up front.
Moving right along to Section 4, the soft touch, Gaussian mixture models.
All right, up until now, all our methods have been, well, pretty rigid. You're either in cluster A or you're in cluster B, no in between. But what if the boundaries between your clusters are a bit blurry or overlapping? The difference becomes super clear when we look at hard versus soft assignments. K-means uses what we call hard assignments. It draws a hard line in the sand. A point belongs to exactly one cluster, period. But Gaussian mixture models, or GMM for short, use a much softer touch. It provides soft assignments. Instead of dropping things into absolute categories, GMM gives you a probability. It might look at a data point and say, hey, I'm about 70% sure this belongs to cluster A, but you know what, there's a solid 30% chance it actually belongs to cluster B. And how does GMM pull off this nuanced approach? It runs something called the EM algorithm, expectation maximization. In the expectation step, it's calculating those exact membership probabilities for every single point. Then, in the maximization step, it updates the shape, the size, and the orientation of the clusters to fit the data even better. Because it's using Gaussian distributions, which are basically just standard bell curves, it has this amazing ability to perfectly model elliptical, stretched out, or even overlapping distributions in the data, things that would completely confuse a standard k-means setup.
Now, for Section 5, choosing your detective tool.
Okay, so we've got a fully loaded toolkit now. K-means, DBSCAN, hierarchical clustering, and GMM. The real question is, how do you actually know which tool to pull out for your specific mystery? Well, this cheat sheet brilliantly organizes the chaos. Check this out. If you have a massive dataset and you suspect the groups are fairly spherical, K-means is going to be your fast, reliable choice. But if you're dealing with weird, irregular shapes and you honestly have no idea how many clusters exist, deploy DBSCAN. If you really need to see a multi-level breakdown and your dataset is pretty small, go ahead and build a tree with hierarchical clustering. And finally, if your clusters are heavily overlapping and you need probabilities rather than hard borders, GMM is absolutely the way to go. Recognizing your data's unique personality is really the secret to picking the right tool.
Bringing us to Section 6, catching the culprit, spotting anomalies.
Now, let's flip the script for a second. The absolute best part about meticulously mapping out what is normal is that it makes it so incredibly easy to catch the culprits that aren't. Unsupervised clustering inherently builds an anomaly detection pipeline for you. Just think about the real-world applications here, spotting a network intrusion or flagging a rare disease marker in a medical scan. It's powerful stuff. If you're using k-means, you just look for those data points sitting wildly far away from any centroid. If you use DBSCAN, the algorithm literally does the heavy lifting for you. You just filter out those noise points we mentioned earlier. And with GMM, you simply single out the points that have a mathematically tiny probability of belonging to any of your bell curves. You map the normal, and the abnormal just completely falls right out into the open.
And that brings us to the end of today's investigation. Mathematics and unsupervised learning can brilliantly reveal these hidden structures. They can spot the outliers perfectly and completely autonomously. But it ultimately leaves us with a truly profound question. If an algorithm is the thing deciding what is normal, who decides what action we actually take on the anomalies? Whether it's a critical security threat, a failing machine part, or a highly unique customer, the algorithm might point the finger, but the human detective still has to close the case. Definitely something to think about as you start analyzing the hidden patterns in your own world. Thanks so much for learning with me today.